Hello all and welcome to Physics with Pranav. If you're new here, I'm Pranav. I'm a former CAIE student who studied science and math. I tutor students from around the world in IGCSE and A-level physics, and I am also an IGCSE world topper from back in 2013. So if you're a GCSE student who is preparing for your physics exam, I can imagine there's two questions that stand at the top of your head. The first is, what are the key topics that are tested so you can prioritize your preparation towards those? And the second is, how do you apply these key concepts in past paper questions? So I am going to introduce to you a three-step, very simple approach that has helped me and my students achieve excellent grades in their GCSE exams. The first step, of course, is to prioritize with data. So I look at recent past papers to try and identify the most commonly tested concepts and topics from each chapter. And then once I have the list of these topics, the next step is to solidify the concepts. So it's essentially saying, right, okay, what are the equations? What are the fundamentals around these concepts that you need to be very clear on so that you would be able to apply them successfully in your exams? And the third step, obviously, is to put those into practice by looking at past paper questions and applying these concepts. So I do have to say that the general advice, obviously, is to study the entirety of your curriculum because you never know when a surprise question is going to make an appearance after years. But if you were being smart in the way you prepared, then you should prioritize your revision towards topics that are most commonly tested in the recent past papers. So that said, I have structured my videos around the chapters of the CAIE IGCSE curriculum. For each chapter, I have made two videos. So the first video will give you a table where I've collected data on the most commonly tested topics, i.e. step one of my three-step process. And I also dive a little bit deeper into these key concepts so you have a solid understanding of those. And then in the second video, of which this is an example, I will walk you through past paper questions for the concepts that we covered in the previous video, right? So the topic of focus in this video is chapter 3, Forces and Motion. And this chapter is ordered and sequenced based on the CAIE IGCSE curriculum. I do have to say that if you are a GCSE student who is not part of the CAIE curriculum, don't worry, because although the chapter numbers may be different, the concepts that are tested across the different GCSE curriculum is going to be pretty much roughly the same, right? So the content that's covered in my previous video, which I've linked below, as well as the application of the concepts to past paper questions, which I'll be covering in this video, will still be really helpful to you. So I hope all of you gain value out of this video. And without further ado, let's go and look at some past paper questions for chapter 3. So before I dive into the papers themselves, I just want to give a quick recap of the most commonly tested questions in these topics. So the first concept you have is around the distinction between mass and weight. I found that every paper 2 had a question around this. So paper 2 is essentially your theory, your multiple choice papers. Paper 4 are your theory papers. So the questions on mass and weight and being able to calculate these concepts and being able to distinguish between these concepts appeared in every paper 2. So if you're very clear on this topic, you will be able to easily score at least a mark in your paper 2, a guaranteed mark. The next commonly tested topic is resultant force and momentum calculations. The resultant force calculations are based around vector addition, and this is again something that I've covered in my chapter notes for this topic of forces in motion. So the link for that video is below in the description, so please feel free to check it out. And this concept is checked in both paper 2 and paper 4. And momentum calculations as well. So how the momentum of different bodies change during an interaction, typically a collision, is also commonly tested concept in these papers. Then, of course, you have the application of force, momentum, and impulse formulae. This is perhaps the most commonly tested topic across both papers, being tested in 15 out of 21 of the past papers I looked at between 2020 and 2022 for paper 2, and around 12 of the 21 past papers I looked at for paper 4 between 2020 and 2022. So it's definitely a very important concept to be aware of. And finally, there is the description of a situation in terms of the change to mass, weight, force, momentum, and or impulse. So the questions on this topic could involve circular motion, free fall, or just general sort of situations like collisions. And again, this is a fairly commonly tested topic in your past papers. So the way I tend to approach these videos as well is I will go through a few of the paper twos, and then once I've done the paper twos, I'll be going through the paper fours. I tend to prioritize the most recent year's paper. So this is 2023. So I'll be going through all of the 2023 variants from both summer, winter, and the Feb-March version to be able to go through these different concepts in those papers. And then once we're done with that, I will be looking at some select paper 4 questions, both from this year as well as previous years, where I think it's a very interesting question and it involves the application of a lot of the concepts that we have looked at in the previous video on chapter 3, forces in motion. Again, link for which can be found in the description below. So if I go to the first paper and going in reverse chronological order, I'll start off with the October-November 2023 paper, and I'm looking at the third variant, which is 2.3 for paper 2. So if I just scroll down, got a few questions on kinematics, got a few questions on volume and kinetic energy, and here you've got a question about force. So it says, an object moves in a circle at constant speed. Which statement about the force needed on the object is correct? So with these types of questions, I like to use the elimination approach, where I look at different options and then I tend to ask myself if it's obviously wrong for some reason, right? I think that's probably the quickest way in which you'd be able to narrow down to your 2 best options usually. So if I start with A, for an object moving in a circle at constant speed, a force that acts away from the center of the circle keeps the object moving in the circle. Now, if we recollect our memory back to the centripetal force always acts towards the center of the circle, and that kind of makes sense. If you think about an object that's moving in a circle, or if you think about, say, the moon moving around the Earth, the Earth's gravitational force is not pulling the moon away from the Earth, or rather pushing the moon away from the Earth, rather it's pulling it towards the Earth, and that's what makes the moon move in a circle. So the force can't be acting away from the center, so that's clearly wrong. The second option goes, a force in the direction of motion of the circle keeps it moving in the circle. Now, force in the direction of motion will keep the object moving in the direction of motion, which is usually tangential to the circle, right? So we did look at this in our notes, but if you remember, if at any point in the circle you have an object that's moving in a circle and you want to know how it would move if the centripetal force was removed, then that object you just have to draw a tangent at that point, and that would show how the object would move if that force is relieved. So that can't be right. The third says a force towards the center of the circle keeps the object moving in the circle. This looks correct, but just, so the thing is, even if you eliminate some options, always good to make sure that, so sometimes the options can be fairly similar, so it's always good to make sure that you do cancel out options, which may be very similar, and that you don't end up selecting the wrong option. So the last one says no force is needed to keep an object moving at a constant speed in a circle. That's not true, because at every point in the circle, the velocity of the object changes, and if the velocity changes, there's an acceleration, and if there's an acceleration, there needs to be a net force. So the no force option is incorrect. So option C is our correct answer here. So then if we go down, that's a question on equilibrium, which we'll be covering in the next chapter. So 7th question. A car of mass 1,200 kilograms is traveling along a straight horizontal road. Which impulse is needed to accelerate the car from 5 meters per second to 10 meters per second? So this is a calculation style question. So in calculation style questions, I like to ask myself what is given to me, right? And what is needed. So they're asking you to calculate the impulse, and they've given you the final velocity, which is 10 meters per second. They've given you the initial velocity, which is 5 meters per second, and they've given you the mass of the vehicle. Now, once I know what I need to calculate, which is the impulse and what I'm given, I try to see how can I link these up. So the impulse is the force multiplied by the time over which the force acts on the body, and it's also equal to the change in momentum. So those are 2 different formulae that you can use to calculate impulse. Now here, you can calculate the change in momentum because you've got the mass of the body and you've got its final velocity and initial velocity. So essentially, impulse is the final momentum minus initial momentum, or the change in momentum. And we know the final momentum minus initial momentum is the mass multiplied by the final velocity minus the initial velocity. Of course, in this case, the mass is not changing, and that gives you 6,000 kilogram meters per second, or it can also be measured in Newton seconds, which, if you think about it, makes sense because Newton is kilogram meters per second square. Yeah, because a Newton is essentially a force is mass times acceleration. Mass is SI units is kilograms, acceleration is meters per second squared. So a Newton would be kilogram meters per second squared. And then if you multiply that by a second, you've essentially got 1 second in the numerator, and you've got a second square in the denominator. So essentially that cancels out to give you 6,000 kilogram meters per second. So you can also use the terminology newtons per second. There's nothing wrong with either. So that is what we've got there. Let me just see if there are any more questions on this topic. No. Again, the general rule of thumb is within the first sort of 10 questions, you will have topics pertaining to force and momentum. So generally, again, if you're feeling very confident about the subject, do look for those questions within the top 10 questions, and then you should be able to find one. So moving on to October-November 2023, paper 2, variant 2.2. If I go down, a lot of these questions are working with speed and motion related questions. There's always one question around like trying to calculate density or volume or any of those, which is covered in topic 1. And yeah, so I've come to question 5 now. It says a satellite orbits the Earth at constant speed in a circular orbit. Which statement is correct? So this again is similar to the question we saw in the previous paper, and it pertains to the centripetal force. So I think a quick way to be able to eliminate options is to see any options where the resultant force is 0. So that's option A. So you can take that out. Any instances where the resultant force is shown to be away from the Earth, that can be taken out as well, or away from rather the object that is the cause for the centripetal motion. And then it can never be in the direction of the motion of the object as well. So I think a quicker way here would be to just see the resultant force is towards the center of the circular motion, and I think that is the quickest option. The resultant force is towards the Earth, and that's the only thing you need to look at. The 0 is out, the away from the Earth is out, and can't be in the direction of the motion as well. So that's how I would look at that. The next bit is a question that, well, it combines both forces as well as moments. We will be covering moments in the next chapter, and I will be making a video on that. But at the moment, for an object to be in equilibrium, the net forces acting on it need to be 0, as well as the net moment acting on it needs to be 0 as well. So again, if I use the concept of elimination, we can see that B and C are definitely out. And the reason they're definitely out is in the case of B, you've got 20 newtons pulling the object upwards and 10 newtons pulling it downwards. That can't be right. In the case of C, you've got, well, it's horizontally balanced because there's 10 newtons opposing each other on the 2 different directions. But vertically, there's just one force acting in a direction, so it's going to move vertically upwards, which leaves us with A and D. So in A, you've got around 20 newtons acting upwards, 20 newtons acting downwards. That seems right. But the thing is, again, as we will cover in the concept of moments, you will see that although the net force is balanced upwards and downwards, there is a turning effect, because essentially the forces that are moving the object in the clockwise direction, so that's the 20 newtons and the 10 newtons, are greater than what is stopping the object moving in the anti-clockwise direction, or rotating rather in the anti-clockwise direction. That's this 10 newtons here. So clearly, while the net forces are balanced, i.e. the object is not going to try and move up or down, it's still going to rotate, which means the object is not in equilibrium. In the final case, if you look at D, then obviously by process of elimination, D has to be right. But if we quickly dive into why that is, we can see that there is 20 newtons there, and then you can see there's 10 newtons here and 10 newtons here. So in terms of the net force acting on the object, that is balanced. But we can also see that the two 10 Newton forces cause turning forces, or cause moments rather, but then they balance each other out. And the 20 Newton doesn't really cause a turning force because it's a central force. So essentially, object D is in equilibrium. Question 7. A resultant force F accelerates a car of mass M along a straight horizontal road from rest to a speed v in time t, giving it momentum p. So which pair of relationships for the situation is correct? Okay, so if we start with A, P multiplied by T is equal to mv. That's clearly wrong because P is the momentum. Momentum is mass into velocity. It's not momentum into time that's mass into velocity, so that's wrong. In the case of B, momentum, that is P is equal to mv. That's correct. And then it says that force is equal to momentum into time. That's not correct. It's rather momentum, or rather the change in momentum, which is equal to force into time. So that equation is not right. In the case of C, momentum is equal to mv. That is correct. And force into time is equal to momentum. Yes, that's correct as well. So typically I would say, yes, you don't have to see D because, there can only be one correct answer. But it's always a good idea to quickly glance at the other option you haven't considered just to make sure that it's not right, or they're not trying to trick you out with this particular option. So if I look at D, its momentum is equal to mass into velocity in time, so that's clearly wrong. So we can have that quick check to say yes, C is the correct answer here. So that's that. I think the other questions are more around work and energy, and again, these are topics that we'll be covering in the future. So next we look at October-November 2023, paper 2-1. If I go down this paper, we've got a few questions on kinematics. And then the first question on forces in motion is, which moving object has a resultant force acting on it? So I think the easiest way to answer these questions, because we know that they seem to be targeting circular motion, is to look for examples where there is circular motion, right? So in the case of B, we can see that the aircraft is circling an airport at constant speed. So that's the example with circular motion here. However, again, to ensure that we're not going to get caught out by some of the other options, if you look at A diver is rising vertically through water at constant speed. The fact that the diver is moving at constant speed and is moving in a singular direction, the direction is not changing, means that is wrong. If you look at C, a train going up a straight incline at constant speed, again, the magnitude remains constant, as well as the direction. It's up a straight incline, so they aren't changing direction at any point. If you look at D, a parachute is descending vertically at terminal velocity. Again, terminal velocity equals constant speed, so there is no net force acting on the object, and they are descending vertically, so again, they're moving in a constant direction. So B is the right answer there. But again, I think usually in these questions, if you see an object that is moving in a circular path, that will have a resultant force acting on it, even if the object is moving at a constant speed. So next, if we look at 6, forces are applied to 4 identical objects. The length of each arrow indicates the magnitude of the force. Which object is in equilibrium? So you've got, again, 4 different options here. So if we look at A, we can see that in A, there are 4 arrows. The arrows to the top and the bottom balance each other out. The arrows to the left and right balance each other out. But the key thing to ask is, do any of these arrows also cause a turning motion? The top and bottom arrows don't, because they act bang on the center of the object. But the left and the right arrows do cause an anti-clockwise turning movement. Now, obviously, we will explore the turning effects of forces, and we will explore the topic of moments in another video. But at the moment, you just need to know that if the forces do cause a turning effect, then the object is still not in equilibrium, even if the magnitude of the forces are equal and in opposite directions. In the case of B, we've got, again, 4 arrows, 2 pointing upwards, 2 pointing to the side. The arrow that points upwards balances the arrow that points downwards, and the force that points to the left balances the force that points to the right. So the object is not going to move side to side or up and down. Is there any rotating effects? And we can see here that all the forces act on the center of the object and are literally parallel to each other. You could have a ruler placed on them and they would literally be in the same line. And that's the case with both the vertical and the horizontal forces. So that basically means that that is the correct answer. But if we quickly just check C and D, in the case of C, there are 2 arrows. Although they are of equal magnitude and in opposite directions, they will produce a turning effect. So there's going to be an anti-clockwise movement. And in the case of D, we can see that the arrow towards the top is greater in size than the arrow towards the bottom, suggesting that there will be a net force upwards. So B is the right answer there. So question 7. A sphere X collides head-on with a second identical sphere Y, which is stationary. The mass of each sphere is 0.15 kilograms. Sphere X is traveling at a velocity of 2 meters per second before the collision and produces an impulse of 0.21 Newton seconds on sphere Y. What is the velocity of sphere X after collision? So I always like to write down what is known and what we need to find in questions that involve calculations. So we know the mass of both the spheres, that's 0.15 kgs. We know that sphere Y is initially stationary, so it has an initial velocity of 0. We know that sphere X has an initial velocity of 2. So we'd be able to find the initial momentum of the system, which is the initial momentum of X plus the initial momentum of Y. Because Y is stationary, there is no initial momentum of Y. So essentially, the initial momentum of the system is equal to the initial momentum of X. And we have calculated that to be 2 into 0.15, which is equal to 0.3 kilogram meters per second. Now, this, according to the principle of conservation of momentum, we know that the total initial momentum, which is also equal to the initial momentum of X, has to be equal to the total final momentum. And we know that the total final momentum is going to be the sum of the final momentum of X plus the sum of the final momentum of Y. Now, although we know the masses of X and Y, we don't know the velocity of either. The only thing we are given as a clue, though, is that when X collides with Y, it produces an impulse of 0.21 Newton seconds on Y. Now, this is an important bit of information because the impact, which is the force multiplied by the time, is also equal to the change in momentum. So here we know that 0.21 seconds is equal to the final momentum of Y minus the initial momentum of Y. Again, you could also do this on X, but I'm just going to do this on Y because it becomes a little bit easier to equate. So we know that the initial momentum of Y is equal to 0, which means 0.21 Newton seconds is equal to the final momentum of Y. So now, by the law of conservation of momentum, we know that the total initial momentum of the system is equal to the total final momentum of the system. I've got that there. And we know that the total initial momentum is equal to the total initial momentum of X, which we have here. So that must equal the final momentum of X and the final momentum of Y. And we've just established that the final momentum of Y is 0.21 Newton seconds. So the initial momentum of X, if we rearrange the equation for that, the final momentum of X, if we rearrange the equation for that, is equal to 0.09 kilogram meters per second. And momentum is mass multiplied by, in this case, X's final velocity. So if we divide 0.09 by X's mass, we will be able to get its final velocity as 0.6 meters per second. And we know here that through the process of elimination, we can take out C and D because that is not 0.6 meters per second. And if you look at A and B, we can see that, one says that the direction of motion is in the opposite direction to Y. The other says the direction of motion is in the same direction as Y. And the key is, sticking to convention, if we say that right to left is essentially positive, we know that X was initially traveling from right to left then because it has a positive value of 2 meters per second. And we know that the impulse on Y is also positive, right? So the final velocity of Y has to act as well. Like if you divided that impulse value by the mass of Y, which is 0.15, you'll be able to find the final velocity of Y, and that will be in the positive direction as well, because 0.21 divided by 0.15 should give you a positive answer. Therefore, the fact that the final velocity of X is also positive means that the final velocity of X must be in the same direction as the final velocity of Y. So the answer is B. Okay, so if we move on to the next paper, we've got May, June 2023, moving into summer now, and we're going to look at variant 2-3. So the first question here, we're talking about a falling object, so it's free fall. So which statement about a falling object accelerating close to the Earth's surface is correct? So some of the things that I would like to remind you here is the fact that accelerating is given means there's a clue, which means the object has not reached terminal velocity, which means the upwards force of drag is not balancing the downwards force of gravity yet. The other thing we know as well is that near the surface of the Earth, the closest surface of the Earth, which is another clue, means that the weight of the object remains the same because the acceleration due to gravity and the gravitational force are constant or can be assumed constant near the surface of the Earth, which means the weight of the object doesn't change unless the mass of the object changes, which is not the case here. So anywhere where we say the weight of the object is changing is incorrect. So we can see in A that it says the weight of the object is increasing. That is not true. And we also know that because the object is still accelerating, we cannot have an equal magnitude of weight and force of air resistance. Therefore, statement B is wrong as well because it says that they are of equal magnitude, which leaves us with statements C and D. So C says the weight of the object is constant, but the force of air resistance on the object is increasing, which makes sense because the weight is constant, that is correct, and the force of air resistance will tend to increase. So there is nothing incorrect about that statement, so that is fine. The last bit that we see states essentially the weight of the object is less than the force of air resistance, which cannot be true because then the object would just get swept up and will be sort of shot away from the Earth, which doesn't really happen. So if we keep going down, there's a question here which says, an object in a space probe above the Earth weighs 3.5 newtons. The gravitational field strength at the height of the space probe is 7 newtons per kilogram. The gravitational field strength on the Earth's surface is 9.8 newtons per kilogram. What are the mass and the weight of the object on the Earth's surface? So first thing that we want to know is we want to know the mass. And the reason we want to know the mass of the object is because once we know the mass, we know it's not going to change, right? So to calculate the mass, we know that weight at a given point is equal to the mass of the object multiplied by the gravitational acceleration or the gravitational field strength at that particular point. So we do know the weight and the gravitational acceleration in the space probe. So if we say force, which is equal to the weight, is equal to mass multiplied by gravitational acceleration, if we rearrange for the mass, you'd be able to find that you get a mass of 0.5 kilograms. So C and D cannot be correct if it's 0.5 kilograms. And once we know the mass of the object, calculating its weight at a different point is straightforward as long as you know the gravitational field strength. So we have been given the gravitational field strength on the Earth's surface, which is 9.8. So if you multiply 0.5 by 9.8, you get a value of 4.9. So that means B is correct and A is incorrect. So if we move to question 6, we've got a cyclist traveling in a straight line along a horizontal road at a constant speed. A constant driving force F acts on the cyclist in the forward direction shown. Which statement about the magnitude of the frictional forces acting on the cyclist is correct? So you have been given a clue here. The cyclist is traveling at a constant speed and is traveling in a straight line. So, and they've got a force F that they are exerting on the bike, which makes the bike move forward, the constant driving force F. So we know that if the object has to travel at a constant speed, there cannot be a net force on the object, which means that if there is a force, a driving force F that's acting forwards and pushing the bike forwards, there has to be a repelling force or a frictional force in the opposite direction that is equal to the force that's driving the bike forwards. So that is the only way the cyclist is going to be traveling in a straight line at a constant speed. So the only statement that can be correct there is that the magnitude is equal to F. So that makes sense. So just seeing if there's any other questions. So yeah, we've got another one. A ball of mass 0.25 kgs hits a wall at a speed of 16 meters per second. It then rebounds back along its original path at a speed of 12 meters per second. What is the impulse experienced by the ball during its impact with the wall? So we know that the impulse is the change in momentum, which is the mass multiplied by the final momentum minus the initial momentum. And if obviously the mass doesn't change, then you can take the mass out and then you can have essentially mass multiplied by the final momentum minus the initial momentum. So instead of multiplying the mass out twice. So in this scenario here, the trick lies in the fact that the velocity is a vector, which means its direction matters, and momentum is essentially a vector as well, because it's a scalar multiplied by a vector. So if we take the left to right direction as positive, and we assume that the wall that is mentioned in the question is here, then the ball that is moving towards the wall essentially has a positive value for its velocity, which is 16 meters per second. And when it rebounds, it's moving from right to left, so in the opposite direction, which means it has a value of negative 12 meters per second. So the mass multiplied by the final momentum minus the initial momentum will be 0.25 multiplied by minus 12 minus 16. Obviously, the 16 is positive, but then you subtract the initial velocity from the final velocity, which is negative. And that gives you a value of technically minus 7 newtons per second. But again, here we are concerned about the magnitude of the impulse, which is why we've got a value of 7 newtons per second. Okay, so if we go to May, June 2023, variant 2.2, the first question is a question on resultant force. You can easily tell if you look at a question that has something like this, it definitely is a question that's testing your ability to add vectors together. So you got forces 3 and 4 acting, 3 newtons and 4 newtons acting at right angles as shown. What is the resultant force? Now, the first thing that you should do is to create the vector triangle. So to create the vector triangle, you need the head of one vector, or the first vector, to touch the toe of the second vector, right? And you'd have a resultant that starts from essentially the toe of the, or the tail rather, sorry, of the first vector and goes all the way up to the head of the second vector. So here, that's what I've done. I've essentially moved the 4 Newton force up there. It's still the same, nothing changes. So that the head of the 3 Newton vector is going to touch the tail of the 4 Newton vector, and the head of the 4 Newton vector is going to be at this point where the y is. And then the resultant will obviously start from the tail of the first vector, which is at point O, and then go all the way to the head of the final vector, which will be at point y. So it has to go from O to y, which means the two options x, z are incorrect. And that kind of makes sense because you've got one vector that is pointing upwards, you've got another vector that's pointing to the right. So the resultant acting on the body would be pointing towards the right and pointing upwards. So that is what we would expect. And then because this is a right angle triangle, these two vectors are at right angles to each other. At least in the multiple choice paper, when you get these types of questions, you would typically get scenarios where the two forces or the two vectors generally are at right angles to each other. So because they are at right angles to one another, you can just use Pythagoras to be able to calculate the length of the hypotenuse, which is also the length of the resultant. And that gives you a value of 5 newtons. So it's a fairly straightforward question. If we look at the next question, a little ball is held at rest at the top of a tall cliff. It is released and falls through the air, eventually reaching its terminal velocity. So which row describes the behavior of the ball as it descends? So I think the first clue is the fact that it eventually reaches its terminal velocity, which means the final acceleration of the ball has to be 0. So it can't be B and D, because in both of those options, the final acceleration is G. And the initial acceleration is going to be G, because it's a light ball, it's held at rest at the top of a cliff, and then it's released, and it's falling essentially close to the surface of the Earth. And that means that its initial acceleration will be G, which is the gravitational field strength near the surface of the Earth. So we've got question 4 next. So which statement about mass or weight is not correct? So masses can be compared using a balance, which is true. So can weight, because you can extrapolate from mass to give you weight. That means A and C are both correct, which means they are incorrect options. Mass is a force. Mass is definitely not a force. Weight is a force. Weight is definitely a force. So therefore, B is the incorrect statement that mass is a force. The next question goes, a sphere P made of steel has a weight of 10 newtons on Earth. Another sphere Q, also made of steel, has a weight of 10 newtons on Mars. The gravitational field strength on Earth is greater than the gravitational field strength on Mars. So which statement is correct? The mass of sphere P is the same as the mass of sphere Q. Now, this statement cannot be correct. And the reason this statement cannot be correct is because, well, let's assume that the mass is m, and then the g has a value of 10, for example, and then that means weight is equal to mg for sphere P, and then P would have a mass of 1 kilogram then. Yep. Now we know that the value of g is lower in Mars because Mars has a lower gravitational field strength than Earth. So if sphere Q has a weight of 10 newtons, and 10 newtons equals mass multiplied by g, but g is less than 10, then when you divide 10 by a number less than 10, you would essentially get a value greater than 1, right? And we did just make out that if you assume that the gravitational acceleration near Earth is equal to 10, then P has a mass of 1 kilogram, and this object clearly has a mass greater than 1 kilogram, so A cannot be right. The second statement says the mass of sphere P is less than the mass of sphere Q, which is what we've deduced, so that is correct, but let's quickly check the other options just to make sure that we don't have any surprises. So on Mars, the weight of sphere P is the same as the weight of sphere Q. That cannot be the case because we've said if we assume that the gravitational attraction on Earth is 10 meters per second squared, then P has a mass of 1 kilogram. Q would have a mass of slightly more than a kilogram at least, because we know that the value of G on Mars is lower than that on Earth. So if P has a lower weight, or rather a lower mass, look at me using standard vocabulary or non-physics vocabulary rather. So because P would have a lower mass than Q, then on any given body, Q is going to be heavier than P. It doesn't matter if it's on Mars, it doesn't matter if it's on Earth, because the mass value is different and the mass value of P is lower than Q. It's only the value of G that changes, and if you're comparing them in the same or on the same celestial body, whether it's the Earth, the Mars, the Moon, Jupiter, wherever you want to do your experiment, you will find that Q will be heavier than P. So they cannot have the same weight. And on Earth, the weight of sphere Q is less than 10 newtons. That can't be true, because again, if we assume by this logic that Q has a mass greater than 1, because the value of G on Mars is less than 10 meters per second squared, then it's going to have a value greater than 1, some value greater than 1, and then if you multiply it by the gravitational field strength on Earth, which is 10 meters per second square, which we've assumed, it's going to have a value of greater than 10 newtons, right? So it can't be having a value of less than 10 newtons, which means B is the correct answer. So in this case, it was fairly straightforward to just go for B, but I think it's always a good idea to check that they don't catch you out with the other questions later down. So question 7, a truck is towing a car along a horizontal road at a constant speed. The road breaks. Which road gives the direction of the initial acceleration of the truck after the road breaks, and the reason for the acceleration? So clearly, the reason this system is moving forwards with a constant speed is because there is a driving force from within the truck. And it is being resisted, obviously, by things like air resistance, by the resistive forces between the tires and the road, as well as by this car. That's like a big sort of load keeping the truck from moving faster. So if the road breaks, the truck, obviously the engine of the truck is going to propel the truck forwards towards the right. So that is going to be the direction of your acceleration. So A and B cannot be correct. And then the reason for that is the fact that its driving force is greater than the resistive force, because now the big resistance that came from the car that was slowing it down is no longer present. So for the same force exerted by the truck, it's going to accelerate. And that's because, again, the driving force is greater than the resistive forces on the truck. So that is the key reason for that. 8 is a question on moments. We'll be looking at that soon. So question 9, a resultant force of 2 Newton acts on an object of mass 3 kilograms for 6 seconds. What is the change in velocity of the object? So I suppose the easier way of doing this would be to say that the force multiplied by the time is equal to the change in momentum. So that would be 12 Newton seconds is going to be the mass multiplied by the change in velocity, or it's going to be 12 is equal to 3 multiplied by delta V, or V minus U, however you want to call it. And then if we divide 12 by 3, we get 4, so V minus U is equal to 4. That is perhaps a simpler way of doing it. The way I've done it here is I've said force is equal to mass into acceleration, and I've substituted the formula for acceleration, which is the rate of change of velocity, or rather the change in velocity by time. We just need to obtain the change in velocity. So we know that the force has a value of 2, the mass has a value of 3, and this happens over a period of 6 seconds. So if we rearrange the formula to make V minus U the subject, we get V minus U is equal to 4 meters per second, or the change in velocity is equal to 4 meters per second. Again, we've got no further questions on the topic. It's usually up to question 10 typically. So if you're feeling confident in this topic, the best thing to do is quickly check up to question 10 to see what questions are covered. So the final variant of major in 2023 is paper 2.1 that we'll be looking at. So that we got a vector diagram again. So we want to know which vector diagram correctly shows force Z as the resultant of forces X and Y. So one of the quick things to check is obviously the way the component arrows are aligned. You can see in both of these cases they're tail to tail, so they're incorrect. So it has to be either C or D because the components are head to tail. And then obviously the next common sense bit, we could use the logical vector triangles and say that, well, the tail of the resultant has to be at the same position as the tail of the first component vector, and the head of the resultant has to be at the head of the second component vector. So therefore, Z is correct. But equally with common sense, you got one vector force acting upwards, you got another vector force acting to the right. So you'd expect the resultant to act upwards and to the right, which is what Z is doing here, but it's not doing that in C. So D is the right answer. If you look at the second question, an object falls towards the surface of the Earth. The object is falling at terminal velocity. If it's falling at terminal velocity, there is no net force, or if there is no net force, there is no acceleration. So we can see here that there are a couple of statements which say the acceleration is negative, so that has to be a no. So A and C are eliminated, and then you have B and D. So in B, we are saying that the acceleration of the object is 0, and there is air resistance, and D, we're saying that there is no air resistance and the acceleration of the object is 0. So we know that, well, there are obviously two scenarios, right, where there is no acceleration, when either net force is 0 or there is no force acting on an object. We know that for a falling object, there is definitely the force of gravity acting on it. So the only way that you would have an acceleration of 0 is when there is another force that is equal and opposite that is acting on the body and resisting its fall. And that is the force of air resistance. So B is the right answer there. Question 3 is a question on kinematics. The next question says, on the Earth, a spring stretches 5 centimeters when a mass of 3 kilograms is suspended from one end. The gravitational field strength by the moon is a sixth that of the Earth. Which mass on the moon would stretch the spring by the same extension? So this question combines the topics of mass, weight, as well as springs. So essentially, in springs, we have a law called Hooke's law, which says that the extension observed in a spring is proportional to the force applied to it until what is called the limit of proportionality. Obviously, I'll make a video that focuses on this topic, and that will be looking at some questions that we saw from this topic as well, as I'm doing now for chapter 3. But the key thing to keep in mind is that the weight is the force here, and it is resulting in an extension. So you've got an object that has a mass of 3 kilograms, and we can assume that it'll have a weight of probably 30 newtons because the gravitational field strength at Earth is close to 10 newtons, and it's 30 newtons that stretches the spring by 5 centimeters, right? So if you're going to have 1/6 the gravitational pull, your force is going to be 1/6 that of what it is going to be on Earth. So you would need a mass that is 6 times as heavy to cause the same amount of force on the moon as you would have on Earth. So to get that 5 centimeter extension, because remember, extension is proportional to the force, you need the same weight acting on the spring. And to get the same weight, you need a mass that's 6 times as heavy on the moon. So if your mass on the Earth is 3 kilograms, then if you multiply 3 by 6, you get a value of 18 kgs. And that's essentially what the mass of the object would have to be on the moon to cause a 5 centimeter extension of that spring. You got a couple questions, one around measurements. You got another one also around measurements, the first topic. Then you got question 7. A train is traveling horizontally in a straight line. So it's either traveling to the right or it's traveling to the left. A book is on a table in the train. The diagram shows all the forces acting on the book. So you got your weight of the book pushing down, contact force pushing it up, equal and opposite. And then you've got frictional force acting towards the right. So obviously the direction of motion will be in the direction opposite to the frictional force. So the direction of motion has to be towards the left, which eliminates options B and D because they suggest that the motion would be towards the right. And then understandably, when there is a force of friction, it will be the case that the object is going to be accelerating, right? Because there is a greater force there, and it is pushing the book closer towards the right than it is towards the it's pushing the object closer towards the left than it is towards the right. Therefore, the object will be accelerating to the left in the diagram. This is a question on moments. Again, we'll be looking at it soon. So question 9, an object of mass 1.2 kilogram is moving with a velocity of 2 meters per second when it has acted on a force of 4 newtons. The velocity of the object increases to 5 meters per second in the same direction. Okay, so the two velocities would, let's assume that they're both in the positive direction, so they would both be positive. And then we want to know the time over which the force acts on the object. So here, essentially, usually when we're trying to calculate impulse, we're trying to think, do we have to use the change of momentum method, or do we have to use the force multiplied by time method? Here, it's going to be slightly different because we can calculate the change in momentum, but we're not interested in the impulse. We're interested in the time that the impulse acts over. So we can get the change in momentum by multiplying the mass of the object into the difference between its final velocity and initial velocity. So that gives us a change in momentum of 3.6 kilogram meters per second. And then we know that the change in momentum is the product of the force and the time. And we know that a force of 4 Newton acts on the body. And again, if we divide the change in momentum by the time, that would give us a time of 0.9 seconds. So that's the time over which the force acts on the object. So again, there's no more questions after question 9. So let's move on to the last paper 2 that we're going to be looking at, which is Feb-March 2023. So we've got a couple of questions on kinematics. So question 4, the drag force on a car increases with speed. At 20 meters per second, the total drag force is 400 newtons. The mass of the car is 1,200 kilograms, and the driving force is constant at 700 newtons. Which statement about the acceleration of the car at 20 meters per second is correct? So let's first calculate the acceleration of the car. So acceleration, so essentially force would be mass multiplied by acceleration. We know that the net force on the car would be the constant driving force of 700 newtons, and the drag force at 20 meters per second of 400 newtons. That's going to be a net 300 Newton force. And that's equal to the mass multiplied by the acceleration. We know the mass. If we divide the force by the mass, i.e. we make the acceleration the subject of the formula, we get a value of 0.25 meters per second square. So clearly C and D are incorrect. And that leaves us essentially with A or B. We've said that the drag of the car increases with its speed. So as the speed of the car increases, you will eventually have more and more drag till at one point you're going to have the drag balancing out the driving force or coming close to it. So you will not have the acceleration increase. That is the acceleration of 20 meters per second, but it will decrease as time passes because it's an accelerating object. The speed increases, and as the speed increases, drag force increases, and as the drag force increases, the net force acting on the body decreases. So look at question 6. An object is rising vertically at constant speed through water. Constant speed meaning no net force. There are 3 vertical forces acting on it: the weight, the drag force, and the upward force. So which diagram shows the magnitude and direction of the vertical forces acting on the object? So again, I try to look for things that I can eliminate. So we can see in the cases of B and C that we've got unequal forces acting in the 2 directions. In the case of B, there's 5 newtons acting upwards and 1 newton acting downwards. So clearly there is a net force. And then in C, there is 4 newtons acting downwards, 2 newtons acting upwards, which means clearly, again, there is a net downwards force. In the case of A and D, there is no net upward or downward forces because the 2 forces balance each other out. They have a value of 3 newtons upwards and downwards. But the clever trick in this question is giving you the clue that the object is rising vertically. So that essentially means that we know that the drag always acts in the opposite direction to the direction of motion. So if the object is rising upwards, the drag has to act downwards. So in the case of A, the drag is acting upwards, but that can't be true because the upward force is upwards and the object is moving upwards. So the drag has to act downwards. So D is the correct answer there. Question 7, again, it's a question on moments. Question 8 is a question on springs. Or question 9, the momentum of a body is changed by a force acting on it for a period of time. Which action increases the change in momentum? Okay, so let's start with the formula for changing momentum, which is the force multiplied by the time. A says doubling the force and halving the time. So let's say that let's assume for the time being that the force is 1 Newton and the time is 1 second. This is something I always like to do in these types of questions. Now we have doubled the force, so now the force is 2 newtons and the time is 0.5 seconds. 2 multiplied by 0.5 is 1. Initially, the change in momentum was 1 multiplied by 1, so it was 1, so there is no change in momentum. If we double the force for the same amount of time, then we've got a force value of 2 newtons and a time value of 1 second, so now we've got a change in momentum of 2 newton seconds. So that is the correct answer, but let's just quickly check the other ones just to be sure. So having both the force and the time, this is probably the worst thing to do, because now you have a force of 0.5 newtons and a time of 0.5 seconds, and that's going to give you essentially 0.25 newton seconds as the change in momentum, which is bad. So it makes it smaller, or essentially makes it a quarter of what it used to be before. And then the last case goes halving the force and doubling the time. That's kind of the reverse of A, where now you've got a force of 0.5 newtons and a time of 1 second. So you've got a total change in momentum of 0.5 newton seconds, which is again half of what it was before. So the only action that increases the change in momentum is doubling the force for the same amount of time. So essentially you want to either double both quantities or double one of the quantities while keeping the other one constant in this case. So those are all the paper twos. I think given sort of the fact that we've done a fair bit of content, what I will likely do is carry out doing paper 4 in a different video. But I hope you found this session useful on paper 2 on topic 3, or rather chapter 3. And if you did, please like this video, consider subscribing, and share this channel with your friends so they can benefit from it as well. Thank you very much.